Problem number 4, example 2.5. Compute the bending stresses in the beam by using the transformed area method. N, or modular ratio, equals 8, and M, or bending moment, equals 110 kip-foot. First, we have to account for the given data based on the drawing. We have here BW, or beam width, that is 18 inches. Next is the height of the entire beam, this one, that is 23 plus 3 inches, that will be 26. Then the B cut, or the width of the cut section, because we have here a cut section above, this is 6 inches, and the height of the cut section is also 6 inches. We have here D, the distance from the outermost compression fiber to the centroid of the steel. This is your effective depth, that is 23 inches. Modular ratio N, we have here 8, and bending moment 110, and we are also given this AS, or total area of steel. This is 4 pieces of number 10 rebar. To solve the problem, let me use a tabulated solution using the solver function or the goal-seek function in Microsoft Excel. Now, in your calculators, you can also use the shift solve function to solve for the value of x. Alright, so to locate the neutral axis, let us have a summation of moment of each area. So that is why we have here A times barred y of all the areas. And then we are going to equate the area of concrete and the area of steel, or A barred y of concrete and A barred y of steel. Alright, so the neutral axis is located somewhere here, and the distance, we designate this one as x. So let me assign this cell C20 as your x, and to emphasize that one, let me shade it with a yellow color. So let's now fill out this table and account for all the data. For area 1, let me consider this one as my area 1, area of concrete without the void. So this is my area 1, and area 1 is B times H, but the H is your X. So let me link this one here, and then H is, we don't know yet, that is your X. So let me link this one to this cell. This one is still a temporary value because we don't know yet the value of X, and Microsoft Excel is gonna compute for X after we have placed all the formulas. Area is simply B times H, and Y, this is our Y for area 1. Let's say the centroid is here, x over 2, at x over 2. So this is x over 2. So x right here divided by 2. And our A times Y, or the moment of this area, is this formula, A times Y, enter. So we have now our values for the first area, or the area of concrete. Now, had it been that this one has no void, then we don't have a problem of the summation of moment. But since we have here a small void, let us account for that area. This one right here. So the B is the B of cut. That will be in inches. And the H of cut, that will also be 6 inches. Then for the area, just drag it, the formula above, so you can refer to this cell and this cell. And then for the Y, this is your Y, the centroid of this area to the neutral axis. And what is that distance? Remember, this is X, and here this distance is 6 over 2. 6 over 2, and this one will be X minus 6 over 2. Alright, so X right here minus 6, or the height of this void, over 2. Now these are temporary values yet, so don't mind the value as of now. And your A barred Y, let me just drag the formula here. That is your A barred Y, referring to the two cells beside it. And lastly, we have area 3. We don't have the dimensions, but we are just given the area. So let's simply encode 5.06. Or you can also refer to this cell equals this cell. And Y is here, the distance from the centroid of the area or the steel to the neutral axis. And since we are given here D from the top to the centroid of the steel, and then this is X, so therefore this is just D minus X, D minus X, or 23 minus X. So we refer to this 23 minus X, that cell. And then A barred Y, or AY, so area times Y, but you must not forget this one, no? For the steel, you have to include the modular ratio. So here, let me multiply to the modular ratio. Alright? Now, to sum up moments, the moments of the area, we have for the concrete, area barred Y, area Y of concrete should be equal to area Y of steel. Steel, and this one concrete. Okay? So therefore, area 1, Y1, but we have here a small void, so minus area 2, Y2, that will be equal to area 3. Okay? Now, let me just transfer the area 3, Y3 to the other side to make the equation compatible for our goal-seek function. So, area 1, Y1 minus area 2, Y2 minus area 3, Y3, that will be equal to 0. So, in this cell right here, let me color this one for emphasis. That will be area 1, Y1 minus area 2, Y2 minus area 3, and it should total to 0. But the answer is negative 823 because we don't know yet X. Now, this is where Microsoft Excel can come in using the goal-seek function, and using your calculator, you can also do the shift solve function. So here, what if analysis, goal seek, set this cell to a value 0 because we want it to be 0 right here by changing this cell. Okay, so if I press OK here, Microsoft Excel is gonna look for a value of X that will satisfy this cell to be 0. Okay, so after several iterations, Microsoft Excel was able to find out that X is 9.32, and this equation will be satisfied. Okay, right here. So this is this equation. So our X now is 9.32. The next step is to solve for I. We still account for the areas, so let me just link it here. Okay, so area is let me alright, so for the B, that will be 18. For the H, that will be 9.32 already. And then IO is BH cubed over 12. So B times H cubed over 12. That is your I of that section. And then for the area, we have B times H. And the Y, we have this value. We just copy that value. And then this one, the total I is the summation of IO plus AD squared or AY squared. Okay, AY squared. So to avoid confusion, let me just place this one as AY squared. Okay, so we have to sum up all the IOs, all the IO plus AY squared here to generate our I. Alright, so IO, this value, plus IO plus A times Y squared. We have that value. Next is area 2. We just refer to this cell because they are the same. Then for the IO, still BH cubed over 12. So I can drag the formula down. Then for the area, I can also drag it down. And then for the Y, I have this value here, 6.32. And then for the IO, I can also drag this formula down. Alright, then for A3 or area of steel, I don't have these dimensions because the steel is not rectangular, and besides, we are not going to calculate for the IO of the steel because the steel is assumed to have 0 stiffness. So let us just consider the area. So here we have the area to be equal to 5.06, and then I will just multiply it with 8 or the modular ratio ahead of time, so that we can always recall that for the steel, the area should be multiplied by the modular ratio. And Y, we know this one already. And then IO plus AY squared, we can just drag it down. And then for the total I, we have here area 1 and then the void, so we deduct minus for area 2 and then add for area 3. So that will be 10,886.94. Okay? Now, we have the neutral axis already, and we have the I. We can now solve for the bending stresses. Okay? So for the I, or for the Y in concrete, that is equal to 9.32 inches. Okay? Because this is just the value of your X, 9.32 inches. And the Y of the steel is 13.68 inches. That is simply equal to D minus X. So we have our Y already, and we have our I. We can solve for the bending stresses in concrete and in steel. So following this formula, FB equals MC over I. This is from strength of materials. We can modify it a bit to fit our concrete design formula. So M, instead of C, we place there Y conc, or Y of concrete. Okay, that is the distance from the outermost compression fiber to the centroid, or to the neutral axis. So plugging in the values, we can generate this answer. Now remember, if what is being asked is the stress, the unit should be in PSI. So right here, the unit of moment is in kip foot. So you have to multiply it by 1012 to make it in pound and inch. So multiply everything by 12,000. Okay? Then for the steel MC over I, but we have here an N, or the modular ratio. So N times M, N is 8, times M, which is 110, then multiply it by 12,000, times the Y of steel, which is 13.68, and divide it by your I, and you will generate this answer. Alright, so that is how to solve this problem.